All right, I think we are recording. So we're gonna do a bit of a final exam review today. As you know, the exam is coming up. So the exam will be in the testing center. It'll be, or no, all right. So force of habit. So it's not in the testing center. It is, but it is open the entire exam week. So it'll be on WebAssign just like it was, just like the midterm was. You'll log into WebAssign. You'll have 5 hours to do it. So from the time that you first open the assignment, that's when your timer starts. So make sure that you're sort of ready and able to sit down, ready to do it. We don't anticipate that it'll take much longer than the second midterm, but we did want to give you an extra hour just because, just in case. So just make sure when you sit down, you have your snacks, you have your water bottle, make sure you use that, do that bathroom break beforehand so you can take advantage of that whole 5 hours, because once you open the assignment, that 5 hours starts and it won't stop until you're done. So it'll be very similar looking to the second midterm. There'll be some multiple choice questions, some true false questions, and some fill in the blank questions. Please read all of the instructions very carefully. There were a number of people who sort of got their grades back, and then they went and they looked and they saw that they had lost points because they hadn't entered. They'd taken, the instructions would say, enter your vectors as column vectors, and they tried to enter them as row vectors or things like that. So the instructions will hopefully be clear enough. As long as you read carefully, it should tell you how we want you to enter, vectors and things like that. I think for this exam, there won't be any row vectors you have to worry about to enter. So I think everything will just be column vectors, but keep that in mind. And then you'll have the entire exam week to do it. And I guess this semester is not really a concern about, long lineups at the testing center. So just find a time that works to take it. Just like the second midterm though, the time stops on the last day of finals at midnight. So even if you start at like 11:30, you're not going to get your full 5 hours. You're only going to get until sort of that exam day ends. So just keep that in mind when you do it. So any questions on anything before we jump into the content and do a practice exam?
Yeah, if that will open Friday.
Yeah. So the exam's open Friday, right? That's when exam week starts. So Thursday is like the reading day, and there's a few exam reviews. So yeah, it'll open on Friday. I'll set it up so it opens at like 12:01 a.m. Friday morning. So yeah.
Will it be on WebAssign again?
Yes, it'll be on WebAssign just like the second midterm. It'll look a lot like the second midterm. It might be a little bit longer, but not much longer.
And it's comprehensive?
It is comprehensive. Now, it will be weighted towards the latter part of the course. The thing with this class is that everything builds on itself. And so we might not, for example, we might not ask you to find, a basis for a null space. But remember, when you're doing things like finding eigenvalues and eigenvectors, you're really, when you're finding eigenvectors, you're really finding a basis for a null space, right? So like we won't maybe ask you as many direct questions from the earlier chapters, although there may be some. But if we ask you to like orthogonally diagonalize or to do an SVD, then you really need all those techniques pretty much anyway. So it is comprehensive, but yeah.
How are we going, where can we go to practice like multiple choice stuff that'll look like the exam?
So the exam questions will be this. So I've posted the practice exam from last semester. I posted the actual exam from last semester, and I posted the practice exam from this semester. All of them have keys. I just got the key for the other one, so I'm gonna post the key soon. But those would be your best place. They won't be formatted exactly like the WebAssign, but because they won't be digital, they'll be on a PDF. But they're the exact same types of questions that we will ask you. Does that answer your question there?
Yeah, thanks.
And those are all posted on Learning Suite under the Content tab. I think we posted them last week sometime. So if you haven't taken a look at them already, definitely should take a look.
Will we have the option to print this one like we did the last one, to work on it like that and just type our answers in?
Well, we probably not. And the reason is because for an exam, that's open for a full week, that was one of the things that one of the other instructors suggested, is not doing that, just because If there's a PDF, you know, there's some possibility that it could be more easily distributed to other students. And obviously, we're not going to be perfect with sort of exam security on this one. Obviously, it's impossible to make an exam entirely secure when it's done online like this. But if there's a PDF that's sort of easier to share, then we probably will try and avoid that. So I think we discussed that, and I think the answer we came to was no. It'll just be sort of displayed on screen.
Okay.
Yeah, sorry about that. I realize it is kind of nice to have the paper like that, but there was just some security concerns we had, so I think we decided not to. Other questions? Now we've exhausted all the questions. All right. So I put together this final exam review slides. I'll post these online as well, so they'll be up soon. These slides, the students always ask for something like this, but I'm always hesitant to provide something like this, and the reason is because it's impossible to create an entirely comprehensive list. And even if I say one thing's on an exam, like it's not always clear, like, you know, if that thing also covers sort of related topics. And so, you know, if I write a list of topics that you have to study, and then there's not a topic that I've listed explicitly, but even though it might be included in sort of another topic, you know, I don't want students to kind of come back and complain that, you know, I didn't say that you had to know this on the review sheet, and so they didn't study it. So this final exam review slides here. Here's a little sort of a disclaimer. Just because it's not written on the slides does not mean you don't have to study it. But these slides are pretty good. I think they'll kind of, this list is pretty comprehensive. I think if you know everything on this list and you're really comfortable with everything on this list, you know, you'll be good for the exam. But just it is possible that something might show up, and it might not be written explicitly on this list, but maybe it's sort of part of something that is written on this list. But so chapter 1. So I'm going to just kind of go through this list pretty quickly because I do want to get to some practiced exam stuff. But we'll just kind of go through this list pretty quickly. So chapter 1, we had quite a bit of, it was all this introduction stuff. So we saw vectors, dot products, orthogonality, norms, and length. And all these topics show up in later sections. So you might not spend a lot of time studying chapter 1 itself, just because all these things kind of come up again. So chapter 2 was where we sort of were introduced to systems of linear equations. And there's kind of two key questions you want to ask whenever you're presented with the system of linear equations. The two key questions are, when will there be a solution to the system of linear equations? In other words, when is the system consistent? And the other question you might ask is, when there is a solution, how do you know if the solution is going to be unique or not? Or is it possible you'll only have one solution, or is it possible you'll have infinitely many solutions? So that's kind of the two key questions you might ask when studying systems of linear equations. And one of the key tools for studying systems of linear equations is row equivalence and row reduction. So we do row equivalence and row reductions in order to take a system of equations that might look very complicated and trying to boil it down to something that's easier to solve, or putting it into row echelon form or reduced row echelon form. Then we saw sort of the first, we saw linear combinations show up for the first time in chapter 2. And we saw that, one key question we could ask is, how do you tell if a vector y is a linear combination of some other vectors, v1 through vp? So that's one question we can ask. We talked about spans, and sort of the important question here is, well, how do you tell when vectors span all of Rn? Okay, so these are a few sort of key questions that we can bring up. We talked about linear independence. How do you tell when some vectors are linearly independent? So those are kind of some key questions. So let me stop here because I can't see any faces. It's hard for me to kind of gauge where people are at with this. But any questions on these first sort of topics we see here? No, it doesn't sound like there are any. Okay. So so spanning and linear independence, these are like two of the big key concepts. So make sure you understand these really well and you kind of have these locked down pretty well. Okay. These are things that'll kind of show up again and again, and they're kind of conceptual things. And so with these two topics in particular, you should know sort of the algebraic definition of what it means for vectors to span or what it means for vectors to be linearly independent. But you should also have a geometric picture in your head. When someone says, oh, these vectors span, you should kind of have an idea of what that means in terms of a picture, okay? Or with linear independence. So, and I mean, that goes for a lot of things. You know, there are a lot of algebraic concepts we define, but there should be sort of geometric intuition that kind of goes back, goes along with them. All right, so moving along to chapter 3, we saw some matrix algebra. We learned about inverses of matrices. So there's, we learned how to find the inverse of a matrix. We learned about various properties of matrix inverses. So for example, one property of matrix inverses you should know is that if you're trying to take the inverse of a product of matrices like A times B, remember, you can simplify this a little bit, but when you want to bring the inverse in, you have to swap the order, okay? So that's one of the things, like where I'd say properties of inverses, that's kind of what I mean there, stuff like that. Or another one would be like, that's not even one, but. Then we have the big invertible matrix theorem here. Remember, the invertible matrix theorem was this huge theorem. It has somewhat like 400 parts or whatever. And all of these parts are basically giving you ways in which you can determine whether a square matrix is invertible or not, okay? Now, I wouldn't memorize this theorem per se, but I would definitely, hopefully you would sort of be able to, we'd never ask you to list everything on this theorem off, but hopefully you'd be able to, by just looking at it, you'd be able to, hopefully looking at the theorem, you can understand why each of those different facts that we have listed on that big theorem is equivalent to the matrix being invertible, okay? So you don't have to memorize part 1, 2, 3, 4, 5, everything, but you do have to know why each of these facts sort of tells you that a matrix is invertible. Then we learned about subspaces. We learned some specific examples of subspaces. So the row space, the column space, and the null space. Those subspaces come up again and again, so it's good to kind of understand those. It's good to know how to find a basis for those. So we learned about bases in chapter 3, and we saw examples of how to find bases of the row space, column space, and null space. We learned about the dimension. So if you remember, the dimension is the number of vectors in a basis for your subspace. We talked about coordinate vectors, rank theorem, linear transformations, and finding the matrix of a linear transformation. So questions on all this? This is kind of the first page. So this is like a good summary of all the different topics we covered up in chapter 3. Any questions there? No?
Can you quickly remind us the process of finding bases for the row, column, and null space?
Okay, good question. So to find a basis for the so each of these has a different recipe, right? So to find a basis for the row space, remember what you do is you take your matrix, right? So you got your matrix A here. You row reduce it down to some echelon form. Say something like this. Okay. And then what you do, if you're interested in the row space, what you do is you look at the non-zero rows, and these non-zero rows are going to be the basis for your row space. Okay. And you take the non-zero rows, you take them from the reduced matrix. Okay. So I row reduce my matrix, and I basically take all of the non-zero rows from the reduced version. That gives me a basis for the row space. To find a basis for the column space, what I do is I look at the pivot columns. In this case, it's the first 2 columns, okay? And then I go back to the original matrix, and I take the corresponding columns from A, and that'll give me a basis for my column space, okay? And then the last one is the null space. What I do then is I row reduce my matrix down like this. And then remember, I kind of pretend like there's an augmented column right here. Okay. And then I basically just solve this system of equations, and I write the solution in vector form, okay? So each of these different subspaces, there's a different recipe, and it's probably the hardest part is just keeping track of, do I want to take the vectors from the reduced matrix, or do I want to go back to the original matrix? And the answer is different depending on whether you're looking at the row space or the column space. Is that okay for whoever asked that?
Yeah, that's great. Thank you.
Okay.
We have some questions in the chat about where to find the YouTube videos or the recorded lectures.
They're all on, I think they're posted on the announcements tab on Learning Suite. Is that not correct? I think the YouTube channel is up on Learning Suite. Yeah, so it'll be the same. It'll be the same as where all the video lectures have been. So if you look at the announcements tab on Learning Suite, or under the announcements on Learning Suite, there is a link to the YouTube videos, and I posted that link way back, kind of middle of March. So that's the same channel we've been using. It's the same place where the Zoom link was posted. So it's just above the Zoom link if you can find that there. Any questions? Other questions?
Yeah, Professor.
Yeah.
Sorry, when you were talking about the column space, I just didn't quite hear you. Did you say that we take the columns from the row reduced matrix that have pivots in them?
No, so the column space, you go back to the original matrix and you take the pivot columns from the original matrix, whereas with the row space, you take the non-zero rows from the reduced matrix.
Okay, thank you.
Yeah, no problem.
Dr. Hughes,
Oh,
can
thanks
we
for
go
sharing
over...
that, Spencer. Yeah.
Oh, sorry. Can you go over linear transformations briefly?
Like what it means to be a linear transformation?
Yeah, or anything.
Okay, so remember, linear transformations are these functions, right? We think of them as like taking a vector. So the way we write it is like this. So you should think of, suppose we give you like a matrix that's like say it's a 2x3 matrix. Okay. Well, if A is a 2x3 matrix, what I can do is I can take a two-dimensional vector and I can multiply it by the matrix A, and that's going to give me a new vector, which is going to be a three-dimensional vector. So I guess it would be kind of hard to go through maybe all the details of linear transformations right now. But remember, we think of linear transformations as being functions, and what they do is they eat in a vector of one dimension, and they spit out a vector of possibly a different dimension. And we can think about a matrix as sort of giving us a linear transformation, and the way that it sort of takes the vector and changes it is that you multiply the matrix by the vector, and it sort of turns it into a new vector with possibly a different dimension. So that's what a transformation is. And then we had, remember we had a few properties that really nice transformations satisfy. So for example, if your transformation satisfies this, and if it satisfies this, so these are two properties. If your transformation satisfies these two things, then we call it a linear transformation, and we can sort of say additional stuff about linear transformations. So I mean, it's a whole section in the book, so it's maybe a little hard to kind of summarize too much more than that without sort of really going into detail. But that's what we were talking about during that section. And does that kind of answer your question, or just does it refresh your memory a little bit?
Yeah, I think.
Yeah, so definitely, I did not provide sort of this is not all you need to know about linear transformations, but hopefully it reminds you what they are, and you can go back and look at them a little bit. So, any other questions?
Can you remind us really quick what coordinate vectors are?
Yeah, so remember coordinate vectors, you take, if I give you a basis, v1 up to vn, right? Then any vector can be written as a linear combination of this basis, right? And what the coordinate vector is you take these weights and you put them as a vector And we call the vector that you build using these weights, we call that the coordinate vector of y. So we use this notation with respect to the basis. Is that okay?
Yeah, that's great. Thank you.
Yeah, awesome. Yeah, so unfortunately I won't be able to a lot of topics here. And so, yeah, I won't be able to give you a really good review of many of these topics in depth just with the time we have. But any other questions there? What I think I'm going to do is, I know you guys have reviews on Thursday. On Thursday, the Math Lab is holding some reviews. Because we probably won't get a ton of review questions covered today, if we're going through these slides here, I'll probably hold a review on Thursday morning. Maybe I haven't just quite decided the time, but we'll hold a review on Thursday morning. We'll go through more questions. So if we don't get to a lot of questions today, that's fine. We'll do some more on Thursday. So chapter 4 is where we were introduced to eigenvalues and eigenvectors. Now remember, there's an algebraic definition of what it means for a vector to be an eigenvector, but there's also this geometric interpretation that you should have kind of in your mind, right? So you should have a picture in your mind, but you should also be able to sort of write down the definition of an eigenvector. Eigenspaces. So remember, the place where the eigenvectors live, those subspaces are called eigenspaces. And you should be able to find a basis for an eigenspace. So when I say find a basis for an eigenspace, this is sort of what we do when we find eigenvectors, right? We subtract lambda off the diagonal, and then we row reduce it down, and we find our eigenvectors. That's exactly what I mean when I say finding a basis for an eigenspace. We talked about determinants. You should know how to compute determinants. You should know properties of determinants. So for example, the determinant of A times B inverse, well, if we break this up, this is the determinant of A times the determinant of B inverse, but determinant of B inverse is the same thing as 1 over the determinant of B. Okay, so you should be able to see something like this, and you should be able to kind of split it up like this. Okay, so that's what I mean when I say properties of determinants. Characteristic polynomials we learned about. We learned about similarity of matrices, and we of course talked about diagonalization. And the key question with diagonalization is how do you know when you can diagonalize a matrix? Okay, and remember, this question of diagonalization comes down to, does every eigenvalue with multiple, every eigenvalue has an algebraic multiplicity, meaning it shows up some number of times as the root of the characteristic polynomial. Well, does that algebraic multiplicity match the number of eigenvectors you find when you look for eigenvectors? If the algebraic multiplicity is, say, 3, and you have an and the eigenvalue only gives you 2 linearly independent eigenvectors, well, because there's that mismatch between geometric and algebraic multiplicity, you know that your matrix is not diagonalizable. Okay, so but there's lots of questions we can kind of ask along that front, basically asking you how to tell whether a matrix is diagonalizable. Questions on this one? No? Okay, so this stuff's a little bit more recent, so you're probably a little bit more fresh with this. Then we did talk about orthonormal and orthogonal bases. We talked about orthogonal matrices. Orthogonal matrices are nice. They have lots of nice properties. So for example, if U is an orthogonal matrix, then U inverse is just equal to U transpose. We know that the determinant of an orthogonal matrix is going to be plus or minus 1. We know that the eigenvalues are going to have absolute value equal to 1, and a few other things. So orthogonal matrices are really nice, and they have a lot of nice properties that you should make sure you're familiar with. We learned about orthogonal complements. We learned about orthogonal projections. Okay, so yeah, we learned about orthogonal complements. We learned how to find a basis for an orthogonal complement. Okay, we learned how to find orthogonal complements for the row space and the column space. So remember, the orthogonal complement of row A is just equal to column A, right? So row A perp is just equal to column A, and vice versa. We learned about orthogonal decompositions. And so when I say orthogonal decomposition, I mean take a vector and we can split it up into a projection piece and a perpendicular piece. We saw the Gram-Schmidt procedure. Oops. Oh, I made a mistake here. This here is supposed to be down here. Okay. I added that in last minute. So we learned about Gram-Schmidt procedure, which tells us, which allows us to take a basis for a subspace, and by doing Gram-Schmidt, even if the basis isn't orthogonal to begin with, we can convert it into an orthogonal basis. We talked about orthogonal diagonalization. And so remember, that's like diagonalization, except we're going to take our matrix A and we're going to split it up into PDP transpose, where P is an orthogonal matrix. Okay, so orthogonal diagonalization is like diagonalization with this one extra sort of condition. We want this to be orthogonal. We talked about the spectral theorem and the spectral decompositions, and then finally in chapter 7 we sort of introduced the singular values and the singular value decomposition. So that's the fresh stuff. So I won't say too much there. But any questions on all of this before we do a few example problems?
Yes. Can you remind me what the orthogonal complement is? I just don't know if I remember that term.
Yeah, so it's this picture. I'll draw the picture for you, and hopefully the picture will help. So it's where you have like a subspace like W, and then you have a subspace like this, where like the two subspaces sort of intersect at a right angle. So every vector you pick on the red thing is going to be orthogonal to every vector you pick on the blue thing. So if that's the case, if every vector in one subspace is orthogonal to every vector in the other, then we would say that those subspaces are orthogonal to each other. And if it's sort of, if they're sort of as big as possible, we'd call it the orthogonal complement. Is that okay?
Yep. Thank you.
Yeah, you're welcome. Other questions? No? All right. Well, in that case, so again, I went through this really quick, and even for some of the questions you asked, what some of these things were, it's kind of hard to get into too much detail just given the amount of time we have right now. But hopefully this gives you a summary, and if there's a topic or two that you don't really remember, you can always go back to the slides or the notes that I posted, and in some cases you can go back to the video lectures and you can remind yourself. So this isn't definitely meant to sort of teach you everything you need to know, but it's more you can use it as a guide to sort of help know what you want to study. Okay. Well, so if there's no other questions, let's talk now. Let's go through the exam from last semester. Okay.
Dr.
So
Hughes,
yeah.
Sorry, I'm not sure if you mentioned this before, but where can we find this guide?
It will be posted to Learning Suite probably in between classes right now. I have to fix a few little. I have to fix like that little ordering issue right there, but it'll be posted. If not right after this class, it'll be posted kind of between 11 and 12 sometime.
Okay, sounds good. Thank you.
Yeah, no problem. All right, so now let's look at an old practice exam. This is the exam from last semester. So it won't be exactly like the exam that we have this semester, but it was written by the same people. So like Dr. Kempton and I wrote this one, and we wrote the last one. So it should be very similar to the one that you'll see. Okay. So let's just go through and do some multiple choice questions. Most people tell me that multiple choice are the hardest. So let's get some practice here. So let's start off with problem 1. Suppose that A is a 7x5 matrix with linearly independent columns. Which of the following statements must be true? Let's mark all that apply. So when I see a question like this, I'm kind of a visual learner. So I like to draw what the matrix kind of looks like. So this is a 7x5 matrix. So it has 7 rows and 5 columns, okay? So it's going to be kind of like a tall, skinny matrix. So I've got 7 rows and 5 columns, okay, something like this. Now, I'm told that I have linearly independent columns, okay? So now what I have to do is I have to connect that to what I know about linear independence. And in particular, what does linear independence tell me about a matrix? Well, if I know that I have linearly independent columns, then that really is telling me that I have to have, will it be a pivot in every column or a pivot in every row?
Column.
Yes. Okay. So that's kind of like the one key fact I need to remember. If my matrix has linearly independent columns, I have a pivot in every single column. Okay. And because of the shape of my matrix, I know I'm not going to have a pivot in every row, but I have a pivot in every column for sure. So let's go down the list now. Now that I've kind of written out what I know, let's go down the list. So the equation, the first option, the equation ax equals b has a unique solution for all b in R7. Is that going to be true?
No.
Why is it not going to be true?
Because there are free variables.
Well, in this case, no, there's not free variables, right? Because we have a pivot in every column, so there's no free variables.
But we don't have a pivot in every row.
Yeah, so this part here is kind of like a double whammy, right? It's really telling you two things. It says it has a unique solution, and because we have no free variables, anytime we have a solution where it's going to be unique, right? But it's also claiming that there's a solution for every single b value. And if I look at this matrix, the only way I'm going to have a solution for every single b value is if I have a pivot in every row. So this matrix does not have a pivot in every row. So therefore, there are going to be some b values for which this equation does not have a solution. Okay. So the unique part might throw you off because you know that, hey, it's got no free variables, but really this is the part that makes it so it's not true. Okay, because there's definitely going to be b values where this doesn't have a solution. So let's cross this one out. It is definitely not true. Okay. Everyone okay on that? Again, I can't see anyone, so again, just feel free to, if you're answering a question or you have a question, just unmute yourself. Just feel free to pipe up. All right, so the next one is the rank of the matrix is equal to 5. What does the rank of a matrix mean? Well, remember the rank of the matrix is either the dimension of the column space or the dimension of the row space. Both of those are always the same. So it doesn't matter. You can either think of it the dimension of the column space, the dimension of the row space. And remember, the dimension of a subspace is just the number of vectors in a basis. And so if we think back to how we find a basis for the column space or how we find a basis for the row space, in each case, when you're finding a basis for either one of these two subspaces, you're going to get exactly one vector in my basis for every pivot in the matrix A. Okay? So if my matrix A has a pivot in every column, which is what we concluded below, and we have 5 columns, it means our matrix has 5 pivots. And so therefore the rank of A is equal to 5. Is everyone okay with that? All right, so the next one is A has 5 pivots, and that's exactly what I just said. So I'm just going to mark that one in. It's kind of a freebie, given what I figured out for the previous part. The fourth option is the columns of A span R7. Is that true or false? Do the columns span or do they not span?
They span
False.
5, don't they?
Well, so yeah, so someone said false and someone said they span R5. So this is a good comment to talk about. So let me write down just what, for example, a column might look like. That's 6. So we have one more, say 2 up there. Okay. So if this were my column, okay. So I think what the one student said is it is false. Okay. So the columns of A span R7. The only way that would be true is if there was a pivot in every single row, right? So having a pivot in every single column tells you that your vectors are linearly independent. Having a pivot in every single row tells you that your columns span, or n or whatever. Now in this case, we don't have a pivot in every row, so we know that they don't span. So, but one student said, well, do they span R5? And you would be almost, I mean, that's almost correct. The thing is though that these vectors in the columns, these are all vectors in R7. okay? So each of these columns is inside of R7. So they can't span R5 because they're not vectors in R5. But if you look at the subspace of these vectors span, it'll be a 5-dimensional subspace. So it will look like R5, okay? But it's a 5-dimensional subspace of R7. So we wouldn't say that it spans R5, but it spans a subspace that's 5-dimensional. Is that okay?
Yeah. Is it true to say that the column space of A spans R5?
Not really true. Like your intuition is spot on. Like so the picture you have in your mind is correct. But again, the column space is kind of like R5, but it's not actually R5. So it's kind of like it's kind of like a picky thing, but I'd rather you have the correct picture in your mind and just say the wrong words than like your intuition is spot on. But we typically wouldn't say it spans R5 because those vectors aren't vectors in R5. Is that kind of okay?
Yes.
But like keep the picture you have in your mind, right? It is a 5-dimensional thing and it looks like R5, but it just happens to live inside of R7. So your intuition is right, and keep that intuition going.
But sorry,
yeah.
the row space would span R5 though, because those are 5.
Yes. Oh, yeah. That's a great comment. Yeah. That's a great thing to add. So if we row reduce this down, maybe when we row reduce this down, we get something like 1 0 0 0 0 0 1 0 0 0. I mean, I guess we know that when we row reduce it down, it'll look something like this. Oops. Okay. And so when you find a basis for your row space, I guess we'll have some more rows of zeros here. Okay. When you find a basis for your row space, the basis you would get is by just taking these vectors here. Now these vectors are in R5, and these vectors here do span R5. And so the row space is all of R5. That's a great thing to add, yeah. Any other questions there, or uncertainties or things that need to be cleared up? No? All right. So let's move on. The system represented by the augmented matrix A equals B is consistent for all B in R7. What do you think about that?
False.
It is false, and it's false for the same reason that we ruled out the first option, right? We concluded that because there's not a pivot in every row, there are going to be some vectors B for which the equation AX equals B has no solution. And that's exactly saying that this augmented matrix will have no solution for some values of B. So this one is false as well. The equation AX equals 0 has a unique solution, true or false? Well, first of all, does it have a solution? Yeah, so yeah, it definitely always has a solution, right? I can plug in x equals 0. So the question is that solution unique? And in order to determine that, I just need to look at whether I have free variables. Because I have a pivot in every column, I know I'm going to have 0 free variables, and therefore I only get one solution. So this one is true. And then the last one, the nullity of A is equal to 2. Who can remind me what the nullity is?
It's
like the amount of useless vectors that you have. They don't contribute anything.
Yeah, it's the dimension of the null space. I mean, there's ways you could think of it as sort of being the number of useless vectors, but it's that you can definitely think of it that way. But it's defined to be the dimension of the null space, okay? And that's the same thing as the number of free variables. Okay. So the nullity is just equal to the number of free variables or the dimension of the null space. And in this case, we have 0 free variables. So the nullity is 0. It's not 2. Okay. Questions on this exam? Yeah.
So the multiple choice questions usually are the one that throw me off. Is there any way we can know how many right answers we have?
How many to look for?
Yeah, because like sometimes we have 2, sometimes we have 4, sometimes all of them are correct.
I don't think we've ever done all of them are correct, if I'm not
I
mistaken.
checked the practice exams, and like there
Uh-huh.
are some questions all of them are correct. Like even in the previous midterms.
Oh, really? Okay.
Mhm.
No, I think, yeah, I think we, I'm surprised that we did give you ones where all of them were correct, because those seem kind of tricky. And so
Uh-huh.
maybe if you could show me where they are afterwards, I'd be interested to see. But
Yeah, I can look to the practice exams and
yeah,
let you know.
yeah, but in any case, I think most of them shouldn't all be correct, and in most of them there will be at least, I would say, in general, they will all either have one solution or one correct one or one wrong one. I think that'd be a little sneaky to put one in that where they're all correct, and so I don't think we would try and do that. Maybe one of them slipped out like that, but yeah, I don't think we can tell you how many are correct or not. So it's kind of you kind of have to evaluate each option just on its own merit and either rule it out or when there is only one correct solution, though, we usually won't put the clover by it, and so so you can always usually be guaranteed there's at least 2 correct solutions. But anyways,
Thank you.
yeah, no problem. So all right, so let's the next one is about an orthogonal matrix, or well, rather, okay, so it says suppose that U is an n by n matrix with orthonormal columns. Which of the following must be true? Mark all that apply. So here we're talking about a square matrix with orthonormal columns. What do we call a matrix that has what do we call a square matrix with orthonormal columns?
An orthogonal matrix.
Yeah. So U is an orthogonal matrix, okay? And that's the terminology that always throws people off, is we call it an orthogonal matrix even though the columns have to be orthonormal, okay? And so there's a few things, like, for example, we know orthogonal matrices, we know that their transposes are the same as their inverses, and a few other facts that we might make use of here. So the first thing is the nullity of A is equal to N. Oh, this is a typo here. Oh, yeah, I don't know if this made it on the final. Okay, so I think A should be U here. And I think A should be U here. That's a typo. I don't know if this is an older version that I'm looking at, but hopefully that was corrected. All right, so the first question is the nullity of U is equal to N. Is that true in this case?
No.
Yeah, correct, it's not true, okay? So it's false. So if a matrix is invertible, so if U is invertible, it really tells you that the null space of U is just the 0 vector, okay? Or in other words, it tells you the dimension of the null space, which is the nullity, is equal to 0, okay? So really the nullity of a matrix, so in this case, we know that U is invertible, right? Because its inverse is just its transpose. So we know that the nullity of it has to be 0. So this first option is definitely false. Okay.
I was thinking when I said like, no, it's not true. I was thinking more that it doesn't have any free variables because they're orthonormal columns, and so they're going to be linearly independent. Is that a right way?
Yep. That's a perfect way to think of it. Yeah. So because you know that the columns are orthogonal to each other, they're non-zero, so they have to be linearly independent. So therefore, every column has a pivot, and therefore there's no free variables, and the number of free variables is the nullity. So again, this sort of leads you back to the fact that the nullity has to be 0. But that's a perfectly valid way to reason your way through it. So that's a good way to think of it. Yeah. U has n non-zero singular values. Is this one going to be true or false? Does anyone know? So this one. So remember, in that big list of the invertible matrix theorem, there's a few facts that tell you whether a matrix is invertible or not. One of those facts is that if a matrix A has a singular value equal to 0, then A is not invertible. Okay, so if a matrix ever has 0 as a singular value, then it can't be invertible. Okay, now in this situation here, we know that our matrix is invertible. Therefore, we know that all of the singular values have to be non-zero. Okay, so therefore this one is true because we know that if it had 0 as a singular value, it would not be invertible. Okay, everyone okay with that?
Yeah, is that also because if there's a singular value that was 0, then also an eigenvalue was 0?
Yeah. So you could actually replace exactly what I said here. Instead of singular values, you could replace that with eigenvalues, and so therefore you could you could say the same thing with eigenvalues, and it would still be true.
Okay. Just wanted to double check.
No, you're good. There we go. So the third option, U, is orthogonally diagonalizable. How do we tell whether a matrix is orthogonally diagonalizable again? Can someone remind me? Well, do we have to go through all the work of finding the eigenvalues, finding eigenvectors, and making sure that the algebraic multiplicity is equal to the geometric multiplicity? Well, the answer in this case is no. Oh, someone was going to say
symmetric, right?
Yeah. So in this case, no. The only thing we have to look for is to tell whether our matrix is symmetric. Okay. So remember, orthogonal diagonalizability is just boils down to whether the matrix is symmetric. Now, in this case, if we know that our matrix is orthogonal, it doesn't have to be symmetric. So for example, here's an example of a matrix which is orthogonal, which is not symmetric. Okay. So this is an example of a matrix that's orthogonal but not symmetric, and therefore this matrix here is not orthogonally diagonalizable. Okay. So this option here would be false. Okay. What about option 4? U is invertible with U inverse equals U transpose.
Yes.
Yeah, so that's kind of what we observed here, right? U is an invertible matrix with U inverse equals U transpose. That's kind of an easy one. U has an eigenvector with eigenvalue lambda equals to 1. Is that going to be true?
Not necessarily.
Yeah, not necessarily. So remember, the eigenvalues of an orthogonal matrix have to be equal to 1 in absolute value. But I could give you an orthogonal matrix like this, right? This matrix here is an orthogonal matrix, but its eigenvalues are all equal to -1. So that's not true. Okay. The length of U times X is equal to U times X for all vectors X in Rn. Is this one true?
Wouldn't it have to be U times X squared?
Oh, like this is equal to this?
If I'm probably remembering incorrectly, but just the U times X squared is equal to the length of X.
No, yeah, I think you might be misremembering that. So U times X squared length is equal to X, the length of X squared. So the squares are equal to each other, but also just these are equal to each other. Yeah, so this was a fact. Oh, sorry, go ahead.
I was gonna say, don't orthogonal matrices not change the length of vectors?
Yeah, so the key thing to remember, the geometric thing to remember about orthogonal matrices is they don't change lengths or angles. So if I have a vector X and I multiply it by the matrix U, the new vector I get is going to have the same length as the original vector. And so that's one of the key geometric facts to remember about orthogonal matrices. And then also the angles don't change between vectors as well, or the dot product of two vectors doesn't change when you multiply them by orthogonal matrices.
Well, isn't that true for orthonormal matrices? But if you have something that's orthogonal, but maybe the basis vectors aren't equal to 1, then it could change the length?
Well, but remember, so this is that weird terminology. We say we call it an orthogonal matrix, but remember it has to have orthonormal columns. So that's just a feature of the weird terminology we use. So whenever I say orthogonal matrix, I am assuming that it has orthonormal columns. Is that okay?
Yep,
Can you
understood.
remind me what the definition of orthonormal is versus orthogonal?
Yeah, so orthogonal and orthonormal are almost the same. The only thing extra that orthonormal has is that each of the vectors is length 1, okay? So for example, a set of vectors like this, say 1, 1, and say negative 1, 1, these vectors are orthogonal, okay? But they're not orthonormal because they have length longer than 1. Is that okay?
Yeah, thanks.
Yeah. So what you could do is you could always take these vectors and you could normalize them, and they'd go from an orthogonal set to an orthonormal set. But back to our list. So this one is true, and that's a fact to remember. The second to last option is that the rank of the matrix is equal to n. Is that one true or not?
True.
Yeah, and that kind of follows again almost from the same reasoning that this one here was false. So the rank is equal to n. We know that there's not going to be any free variables. We know that every column has to have a pivot, and therefore the rank is n. The last one is the matrix U has orthonormal rows. Any guesses on that one? So this is true, and it's a fact. It's just a fact from a theorem that we saw. And you know, if a matrix U is orthogonal, we already know it has to have orthonormal columns. That's kind of like the definition. But what's maybe less obvious is that it also has to have orthonormal rows. Okay, but if you make the columns orthonormal, then the rows will be orthonormal automatically. So
by transposing the A inverse equals A.
yeah. You cut out a little bit there, but I think what you're saying is correct there. From the little bits, you basically take the transpose, you show that matrix is also orthogonal, and then therefore its columns have to be orthonormal, and therefore the rows of the original are orthonormal. All right, any questions there? All right, so we are over time. I'm going to pause this recording just for a bit. We are going to start another lecture in like 3 or 4 minutes here. I will continue going on with the same questions, but I will go over those review slides again, just because there will be new people coming in. So I will be posting these videos online, but I will kind of be going over those review slides each time. So if you don't want to sit through that part again, you don't have to stick around. But if you want to stick around, once we get through those review slides again for the new people, we'll kind of continue where we left off on this exam here. So, and then again, remember, I will hold a review session starting, I'll hold a review session Thursday morning, and I'll announce that time sometime later today. So I'll sign off for just like 3 or 4 minutes here. I've got to fix one thing in the slide, and then I'll pick back up in a couple minutes here. So